Okay, now I would like to explain about the self-inductance, mutual inductance and the quotient of coupling. So first one, self-inductance, it is represented by capital L. Units are henries. So let V of t be an alternating voltage applied across it. This is inductor and this inductance value equals to L. Here this inductance is called self-inductance. So V of t is applied voltage and I of t be the alternating current flowing through it. So V of t alternating voltage, applied voltage, I of t the alternating current flowing through this inductor or coil. So as soon as the current passes through the coil, a flux pi of t is set up across it. Okay. So generally we know that the current carrying conductors produces the magnetic flux. So here I of t current flowing through this coil. This coil is one inductor. So the inductor property. So the inductor stores the electrical energy in the form of magnetic flux or magnetic field. So here the pi of t flux is set up across it. So since this flux is also alternating, EMF will be induced in it according to Faraday's law of electromagnetic induction. So here the flux type is alternating. So according to Faraday's law of electromagnetic induction, so whenever a stationary conductor placed in a time varying magnetic field, an EMF is induced across the conductor. Here applied voltage alternating voltage, so applied current also alternating current. So finally this coil produces the alternating flux. So because of this flux and a stationary conductor, so according to Faraday's law of electromagnetic induction, an EMF is induced across this coil. This induced EMF equals to E of t. It is represented by E of t. So V of t applied voltage or generated EMF or induced EMF equals to E of t. So here E of t value directly proportional to d by dt of I of t. Okay. This EMF is depends on rate of change of current, or E of t equals to L into di by dt. So generally we know that the current produces the magnetic flux. So pi of t directly proportional to I of t. So we can write this equation E of t proportional to d by dt of pi of t. The current produces the magnetic flux. If current increases, magnetic flux increases. If current decreases, magnetic flux also decreases. So E of t proportional to d by dt of pi of t, or E of t equals to n into d pi by dt. Here capital N is number of turns. Here L is self-inductance. Now by equating equations 1 and 2, L into di by dt equals to n into d pi by dt, or L into di equals to n into d pi, L equals to n into d pi by di, or L equals to n into pi by I, henries. Okay. So d pi by di we can write pi by I. So finally the self-inductance L equals to n pi by I. Here n is number of turns, pi magnetic flux, I current flowing through the coil. So generally the flux linkages is called number of flux linkages equals to number of turns into magnetic flux. Here numerator n into pi, number of turns into magnetic flux, it is called flux linkages. So the self-inductance is the ratio of the flux linkages and current. The ratio of flux linkages and current is called self-inductance. So units are henries. So next one, mutual inductance. So consider two coils placed nearer to each other as shown in figure. Okay, this is the figure. Here two coils placed nearer to each other. This is first coil and this is second coil. So let N1, N2 be the number of turns of coil 1 and 2. Let I1 be the current flowing to the coil 1 when alternating voltage V1 is applied across the first coil. Let M be the mutual inductance between the two coils. Okay, generally the mutual inductance is present. So whenever two coils are placed nearer to each other. Here two coils placed nearer to each other. So here exists the mutual inductance. So the circuit having two self-inductances, two mutual inductances. Okay, first coil self-inductance value L1, second coil self-inductance value L2. So first coil to second coil mutual inductance equals to M12, second coil to first coil mutual inductance is M21. Here applied voltage is V1, alternating voltage. I1 is applied current, alternating current. So next V2, the voltage across the second coil. Here E1 is the induced EMF across the first coil, and E2 is the induced EMF across the second coil. So as soon as the current starts flowing through the coil, a flux pi1 is set up in the coil 1. So here, because of this current I1, a magnetic flux produced across the coil 1. So coil 1 magnetic flux equals to pi1. Since the coil is cutting the flux and EMF E1 will be induced in the coil. So according to the Faraday's law of electromagnetic induction, so whenever a stationary conductor placed in a time varying magnetic field, an EMF is induced across the conductor. So based on that principle, here time varying flux is present, and in that flux this coil is placed. So according to Faraday's law of electromagnetic induction, in first coil an EMF is induced. This EMF equals to E1. So next, since the second coil is placed nearer to first coil, here second coil is placed nearer to first coil, say part of the flux, here first coil flux equals to pi1. This total flux pi1, and this in total flux pi1, some part of flux pi1 to links with the second coil. Okay, part of flux pi1 links with the second coil, and according to Faraday's law of electromagnetic induction, again EMF will also be induced across the second coil. The magnitude of the induced EMF E2 in second coil is given by, so E2 proportional to dI1 by dt. Here input current or applied current equals to I1. So this I1 current produces the magnetic flux pi1. This, because of this pi1, in first coil some EMF is induced. This EMF is E1. Some part of the flux, here two coils are placed nearer to each other, so some part of the flux that links with the second coil. So due to these flux linkages, in second coil also some EMF will induce. This induced EMF is E2. This induced EMF value directly proportional to this current, the rate of change of first coil current. So E2 proportional to d by dt of I1, or E2 equals to m into dI1 by dt. Okay, m into dI1 by dt. Okay, equation number 1. Okay, we know that the magnetic flux directly proportional to current, so we can write E2 proportional to d by dt. Here pi1 to flux links with the second coil, so d by dt of pi1 to. Okay, due to this pi1 to flux only, EMF E2 induced, so E2 proportional to d by dt of pi1 to, or E2 equals to N2 into d pi12 by dt. Here N2 second coil number of turns. Now by equating equations 1 and 2, we can write m into di1 by dt equals to N2 d pi12 by dt. So both sides dt cancel. M into di1 equals to N2 into d pi12, or m into I1 equals to N2 into pi12, m equals to N2 into pi12 by I1. So m equals to N2 means second coil number of turns, pi1 to first coil flux that links with the second coil. Okay, part of the first coil flux that links with the second coil is pi1 to, I1 is first coil current. Here numerator flux linkages. So flux linkages in second coil due to first coil flux, numerator. Denominator is first coil current. So this is called mutual inductance. The mutual inductance is represented by, the units are henries. So similarly, in the first coil, okay, so if for example, the first coil induced EMF E1 proportional to E1 proportional to di2 by dt. Okay, here in previous case, here the applied voltage equals to P1 and supplied current equals to I1. Here flux first produced is pi1. So because of the flux pi1, E1 induced, and part of the flux pi1 to that links with the second coil. Next EMF E2 induced. Okay, now assumption, here supply connected at second coil, supply connected across the second coil V2, and second coil current equals to I2. So now in second coil the pi2 magnetic flux produced. So due to this flux in second coil EMF induced, it equals to E2. So part of the second coil flux, okay, pi2 1, part of the second coil flux that links with the first coil is pi2 1. So due to this pi2 1 flux in first coil, some EMF induced, that EMF is E1. So E1 proportional to second coil, the rate of change of second coil current. Okay, in this case we are connecting supply across the first coil. In second case, now we are finding another mutual inductance. So assumption, the supply connected across the second coil. So that supply equals to V2. So in first coil, EMF induced, it equals to E1 proportional to d by dt of I2, or E1 equals to m into di2 by dt, equation number 3. In terms of flux linkages, so E1 proportional to d pi to 1 by dt. Okay, pi to 1 is part of the second coil flux that links with the first coil. So E1 proportional to d by dt of pi to 1, or E1 equals to n1 into d pi to 1 by dt. Now by equating equations 3 and 4, we can write this equation: n1 into d pi to 1 by dt equals to m into di2 by dt. So dt cancel. n1 into d pi to 1 equals to m into di2. So m equals to n1 into pi to 1 by I2. Okay, this is the mutual inductance between second coil to first coil. So now the quotient of coupling. So it is represented by K. So K value always lies between 0 to 1, K maximum value 1, K minimum value 0. So the fraction of total flux which links with the other coil is called quotient of coupling. So K equals to pi 1 2 by pi 1. Here pi 1 2 is first coil, part of first coil flux that links with the second coil is pi to 1. So next pi to 1 is part of the second coil flux that links with the first coil. So K equals to pi 1 2 by pi 1, or it equals to pi to 1 by pi 2. So the value of K equals to 1. The coupling between the two coils is 100%. It equals to 0. Coupling between two coils is low. So n equals to n1 pi to 1 by I2, or n2 pi 1 2 by I1. Okay, these two mutual inductance formulas. So by multiplying above two equations, m square equals to n1 pi to 1 by I2, n2 pi 1 2 by I1. Okay, multiply and divide with pi 1. So pi 1 by pi 1 into pi 2 by pi 2. So it equals to n1 pi 1 by I1, n1 pi 1 by I1, n2 pi 2 by I2 equals to pi 2 1 by pi 2, pi 1 2 by pi 1, or m square equals to L1 into L2, K into K, or m square equals to K square into L1 L2, m equals to K into square root of L1 into L2, or K equals to m by root L1 L2. So K is called quotient of coupling. K value constant value. So K value always less than 1. If K equals to 1, so the circuit is called tightly coupled circuit.